Hello, ladies and gentlemen. We are now back and talking about power analysis and AC circuits. So we're going to go through instantaneous power, which is the same as DC, current times voltage. Then lots of things related to AC, average power, RMS values, how they're related to power and power correction factors and so forth, so that we can handle AC power. There's some tweaks. There's some differences when you're talking about AC power versus DC. So we start out with instantaneous power. Just like DC, you take your voltage, AC current, multiply the current voltage together to get instantaneous power. And so when we multiply it together, we get this expression here. Now, we're going to need to simplify this expression, and we use this trig identity. I wanted to show how we derive this trig identity. If you add these two equations here together, you'll get twice cosine phi 1 cosine phi 2, which is this side of the equation. Adding these two together is just what's in brackets, and the signs, when you add them together, cancel out. So you can see how we get from our trig identities we know to this new one. I like to show the math behind things a lot of times. Applying this trig identity, we get cosine of the difference of the phase angles as a multiplying factor, and then cosine of twice the frequency plus a new phase angle. So if you have voltage at this expression for voltage and the impedance, you want to find the current and the power. Voltage here is going to equal 4 angle 60. 4 angle 60 in the phasor notation. So we can get the current is going to be V over Z given by this. Now, we can't just use phasors to add these two together. We got to use this formula here to get instantaneous power. So we go there and we start writing things down. So now the power is going to equal, well, phasors are still good for voltage max and current max magnitude, and you just have the omega t's. And then the rest of the power we get from this equation. Vm Im over 2 cosine of the difference between the two angles, 60 and 30. Well, the difference is 30. And then the product of the 2 over 2 again. 4 times 2 over 2 is 4. Cosine twice omega t. There's the twice omega t. And the sum of the angle, the current angle and the voltage angle. 30 gives you 90. So that would be the power, instantaneous power at any given time. We have a constant term, and then we have a time varying term. Let's take a look at this. So here's a plot of voltage, a plot of current, and then a plot of the power. Varies at twice the frequency of the current or the voltage. Constant term, here's the point. Constant term here. Time varying term. When you do the averaging, the average of the cosine is going to be 0. So average power will just be the constant term. Okay, moving on. In fact, that's the next topic. So we average over one period of time, And when we do that, this is the average power. It doesn't matter who leads, because the cosine of theta equals the cosine of negative theta. So the power doesn't care which is the leading, which is the lagging factor, whether the voltage or the current leads. If they're exactly in phase, which is like a resistor, the power is just 1/2 maximum times maximum. Now remember, Vm is the amplitude of a sine wave. And if Vm and Im, Vm, Im, where this is either V or I, you have a sine wave, and this is the zero, the horizontal axis. When you multiply the two together, you get a waveform that looks like this, if they're in phase. So this, it turns out, the mathematics of a sine wave, that you get this 1/2 factor. You can take, in DC power, of course, you'd have this, Vm times Im. AC power, though, you're not consuming power here. Your power has dropped in these regions, and it turns out the factor that you use is 1/2. So this is average power as a function of the peak voltage, not the average voltage, and the peak current. Just trying to hammer that point a little bit. If they're exactly 90 degrees out of phase, then the average power is going to be 0. Now from this factor right here, 90 degrees out of phase. So here we have purely resistive, purely capacitive, or inductive. Power is not consumed on average by an inductor or a capacitor. Okay, so let's find the average power consumed by this. And we need the impedance 2 plus 2J ohms, and we know the voltage, so the current is going to be I know what this is. It's the square root of 8, or 2 square root of 2. 2 square root of 2 at an angle of 45. Angle 45 degrees. Okay, so current is going to be 10 angle 60 degrees over 2 square root of 2 angle 45 degrees. Equals 5 square root of 2 over 2 angle 15 degrees. And then, so now we know the voltage here, the current here. We can just multiply the two together. That's power average is going to equal the power is going to equal 1/2 VMIM, which is 10 times this factor here, which is going to be 25 square root of 2 and then the cosine of the angle of the difference between the angles. So that's 60 minus 15, or the cosine of 45 degrees. Well, the cosine of 45 degrees is 1 over the square root of 2. So the answer is 12.5 watts. Just remember, 12.5 watts, how we got there. I is, yeah, that makes sense. 3.53 is pretty close to 2 root, or 5/2 root 2. Okay, I'm going to get rid of my ink on the slide just so you guys can see better. Just remember what we did, write it down or something like that. Okay, so here's what the book does. VM, IM, okay. 12.5 watts, just like we figured out. Voila. Okay, next video.